Hello everyone. In this meeting, we will read together the paper DHSA on efficient doubly homomorphic Skew aggregation for the cross-silo federated learning. So let's start by the abstract. So the Skew aggregation is widely used in horizontal federated learning to prevent leakage of training data when model updates from data owners are aggregated. The Skew aggregation protocols based on homomorphic encryption have been utilized in industrial cross-silo federated learning systems. One of the settings involved with privacy-sensitive organizations such as financial or medical presented more stringent requirements on privacy security. However, existing homomorphic encryption-based solutions have limitations in efficiency and security guarantees against the clothing adversaries without a trusted third party. This paper proposed an efficient doubly homomorphic Skew aggregation DHSA schema for the cross-silo federated learning, which utilizes multi-K homomorphic encryption and a seed homomorphic pseudo-random generator. As cryptographic primitive, the application of multi-K homomorphic encryption provides strong security guarantees against two numbers participate. Clothing with aggregation with no TTP required to mitigate the large computation and communication costs of the multi-K homomorphic encryption, will leverage the homomorphic property of the seed homomorphic pseudo-random generator to replace the majority of multi-K homomorphic encryption computation by computationally friendly mask generation from a seed pseudo-random generator, while preserving the security. Overall, the resultant schema satisfies the stringent security requirements of typical cross-silo federated learning scenarios, at the same time providing high computation and communication efficiency for practical usage. We experimentally demonstrate our schema brings a speed up to 20% over the state-of-the-art homomorphic encryption-based Skew aggregation and reduce the traffic volume to approximately 1.5% inflation over the plain learning system. So we can understand that this paper presents a Skew aggregation protocol based on a doubly homomorphic Skew aggregation. The doubly homomorphic Skew aggregation means this doubly means the use of which utilizes two kinds of the homomorphic encryption. The first one, which is the multi-K homomorphic encryption, and the second one, which is the seed homomorphic pseudo-random generator. So those two techniques gives strong security guarantees, and also one of this disadvantages of using the doubly homomorphic Skew aggregation is the large computation and communication cost. So to solve this problem, they propose to replace the majority of multi-K homomorphic encryption computation by computationally mask generation from a seed homomorphic pseudo-random generator, while preserving the security but reducing the time, computation, and communication. So this is what we understand from the abstract. Then, like, we will not pass more time. We will see, we'll see then materials and methods. Here in the conclusion, we have that this paper presents a doubly homomorphic skew aggregation schema for the cross-silo federated learning setting. We present the application of multi-K homomorphic encryption, which can achieve the stringent security goal of cross-silo federated learning against colluding parties at a maximum degree, and to overcome the bottleneck of high overhead, we utilize the seed homomorphic pseudo-random generator to reduce the volume of data that needs to be computed securely via the multi-K homomorphic encryption. So overall, we construct a practical privacy-preserving aggregation solution combining the seed homomorphic pseudo-random generator based on homomorphic model aggregation protocol and multi-K based masking seed aggregation protocol, which is demonstrated to achieve the requirement of a practical and secure cross-silo federated learning system from the security, efficiency, and accuracy aspect. So the privacy security provided by our schema is robust to the server colluding with up to two clients, which can be reached without the need for the TTP. Our solution improves the computation efficiency up to 20 times over the baseline experimentally, and the communication overhead is reduced significantly. Meanwhile, additionally, the security and efficiency are provided at no cost of the accuracy of the global model, enabling the practicality of industry deployment. So now we need to have like a deep view on the multi-K homomorphic encryption, also the seed homomorphic pseudo-random generator. So for that, uh, those experiments. This is the second part, which is the masking seed aggregation protocol. We'll have a look on the first one first, which is homomorphic model aggregation protocol. Yeah, this is it. So we'll have a look on this part, which is the overview of the doubly homomorphic secure aggregation schema. As discussed above, so the doubly homomorphic secure aggregation is constructed with two layers of protocols. Okay, the model updates are securely shared and aggregated following the homomorphic model aggregation protocol, which calls the masking seed agreement protocol to return the demasking seed to the client and enable the demasking to obtain the global model update, which is described in Figure 1, the combination mechanism of two layers of protocols. So we have here the client, we have here the client, then this is the homomorphic model aggregation protocol. So it starts from central server by creating the masked model aggregation. So each client creates the masked model, then send it to the central server, then the central server makes the aggregation of the masked model and then resend it to the other clients. After that, there is the masking seed agreement protocol, which so the combination of the two protocols which guides the following design of Doubly homomorphic secure aggregation, the most straightforward construction to build secure aggregation. Okay, for every epoch T where the homomorphic masked aggregation is performed to do the aggregation of model updates. The MSA masked skew aggregation. So we have the homomorphic masked aggregation and okay, so let's look on that deeply. So here we have a combination of the two protocols. The first protocol, which is the homomorphic masked aggregation, then the masked secure aggregation. So, which guide the following design of the doubly homomorphic secure aggregation. The most straightforward construction to build secure aggregation is that for every epoch T, where is T? Like for every epoch, those ones, T, where the homomorphic masked aggregation, which is this one, homomorphic model aggregation, okay? Homomorphic model aggregation is performed to do aggregation of model updates, which is this first part. This is the homomorphic model aggregation. It's this first part, like here, okay? Then the masked secure aggregation, which is this part. So we have the red one and the black one, is called once to provide the current, the masking seed. Recall that in the cross-silo scenario, all participating clients remain available during the whole interactive learning process of federated learning, which means the model aggregation and the homomorphic model aggregation protocol for every epoch is over the same set of clients. As a result, the demasking seed, okay, the second parts for all involved epoch correspond to the same set of clients, of course. So this masking and demasking seed for multiply epoch unity list and the homomorphic model aggregation protocol can be prepared in advance, which is figure 2. So let's have a look on this, the overview of doubly homomorphic skew aggregation. So this is the algorithm. So the assumption is we have an N client jointly train a DNN model whose number of trainable parameters is M. Under the coordination of the server A, the number of masking seed pairs agreed and pure masking seed agreement protocol is P. While the model has not converged to desired performance, which means masking seed agreement protocol. Okay, so then for the training epoch, we should have the homomorphic model aggregation protocol. Okay. So while the model has not converged to desired performance. Okay. So the input here is the QA, which is the masking seed agreement from each client, and output is K0, which is to each client. Okay. This will be done on the server. Then we have here the homomorphic model aggregation protocol. As input, the list of model update and masking seed pairs. The list of model updates. Okay. And masking seed pairs from each client. The output is aggregation of all client model updates to each client. If the model converges to the desired performance and the for loop. Okay? So depict the overall process of the mechanism. The model seed protocol is firstly carried out to set up the masked seed pairs for a epoch. Masked seed pairs, which are consumed in the next round of the homomorphic model aggregation. Okay, protocol. If the federated learning training convergence within P epoch, the execution is ended. If not, all the participants called the masked seed aggregation protocol another time and repeat the steps until the convergence is achieved. Okay. This construction can be implemented more efficiently because we take advantage of the SEMD technique of BFV by packing multiple masking seed in one BFV suffix. In addition to the SEMD optimization, we can evaluate multiple suffix in one execution. Evaluate multiple suffix in one execution of the multi-seed aggregation protocol. So as a result, only a single round of communication is required for each learning epoch. So, of the federated learning to perform the homomorphic model aggregation protocol, it's sufficient to perform the masked seed aggregation protocol. So as a result, only a single round of communication is required for each learning epoch of federated learning to perform the homomorphic model aggregation protocol. It's sufficient to perform the masked seed aggregation protocol. So it's clear now. Once every P epoch, which significantly reduces the number of rounds of communication for the federated learning process with a total of T epoch. If T is not bigger than P, the masked seed aggregation protocol is executed once. Okay, then otherwise it's executed for T multiple P times. We can adjust the C10 of P to match different federated learning application. Next, we will describe the homomorphic model aggregation and the masked seed aggregation protocol in detail, respectively. So let's start first by the homomorphic model aggregation, which is this first one, okay? Like this first one. So, in the homomorphic model aggregation protocol, the aggregation of client local model is computed under the orchestration of the server, okay, which is logic, ensuring no information about the individual models is revealed beyond their aggregated value, which is figure 2, the homomorphic model aggregation. So it starts by the parameters, a random matrix. Then the input, we have the masked U of each client and the K of each client. The output, which is M0 for each client U. The first step is pre-process the model update MU and encrypt the quantized model update XU to return this one. Then the second step is to upload the YU to the server. Then the server collects the value of all clients and do the aggregation to return the Y0 for the others clients. Then broadcast the masked aggregation results to all online clients. Then client U, after receiving the Y0, decrypts it by computing X0, where K0 is returned by the masked K aggregation protocol. Then dequantize X0 to obtain the final aggregation model update. Okay, so this is homomorphic model aggregation. So shows the homomorphic model aggregation protocol over the online client that constructs the set of n clients. Each client first locally samples a random masking seed as the input. Okay, each client first locally samples a random masking seed as the input to the seed homomorphic pseudo-random generator. Okay, and stretches it to a mask for all entities of the model update. Okay, then they upload the masked model update to the server. Okay, they upload masked model update to the server. The server aggregates the uploaded data of online clients and broadcasts the Y0 to online clients who receive K0 from masked seed aggregation. The client removes the mask, which is GK0 from Y0, and dequantize the result before computing the average to obtain the updated global model. Besides malicious clients combining the uploaded data from different epochs may induce information leakage about individual clients. To address this threat, clients apply different masking seed in different epochs to obtain disposable masks. We instantiate the protocol by the almost seed homomorphic pseudo-random generator introduced in section 2. Since the output of the seed homomorphic pseudo-random generator is an imaginary. Okay, we set the public modulus P in our schema equal to P, and the model updates are processed by the quantization operation, which converts each bounded local model update to W-bit integer before adding masks for a model update M and in the quantized value. Okay, where is A? Is the Florin functions that maps A and R to the largest integer not greater than A. The aggregation of quantized value over n parties is at most. So we set to make sure the summed model update does not overflow. For summation result X, the corresponding dequantization is performed by. Then we have the second part, which is the masked seed aggregation protocol and the masked seed agreement protocol. The server and client jointly compute the demasking seed, which are the sum of the masking seeds of corresponding clients. The input of the masked Skew aggregation protocol are masking seeds for T epoch for each client U, where the KTU is generated independently by the client U for epoch T and kept private by the individual. The demasking seeds for T epoch K0 are computed and released to only clients without revealing the individual masking keys, which is achieved by the compact multi-K techniques. As illustrated in Figure 4, the first step of the protocol is key generation to set up the common public key and the re-encryption key. Each client generates a pair of secret and public key individually, and the common public key is computed for encryption based on the individual public key. Here the same public parameter is taken as the input of the key generation algorithm so that the multi-key homomorphic arithmetic is supported. For a client U, after the individual key pair obtained, it uploads the public key to the server. The server combines all received public key to return a common public key and broadcasts it to all the clients for encryption. Also, one leader client generates the re-encryption key pair and releases it to other clients who have access to the final decryption in a secure manner. The Diffie-Hellman key agreement technique and authenticated encryption can be combined to prevent revealing the re-encryption key pair to any external party, including the server. It's not the core of our work. Okay. So implementation details are omitted here. The re-encryption secret key should be kept private by clients, who are the model receiver. To verify the validation of the re-encryption key pair, each client performs encryption and decryption on the received key pair to check the correctness of the decryption results. After the generation, the participants perform 2 rounds of communication for encryption, evaluation, re-encryption, and the final decryption. In the first round, each client encrypts the masking seeds with the common public key before sending it to the server. Then the server aggregates all the received ciphertext to return the encrypted sum over all masking seeds, which is CT, under the joint secret key. And the next round, the client and the server execute the public key switch protocol to re-encrypt, outputting the ciphertext which can be decrypted with the re-encryption secret key. Finally, a related client utilizes a secret key to decrypt the received ciphertext and obtain the demasking seeds. Okay. Then we will check the correctness and the security. So we'll have another look on this because it's the first time that I read this paper. So it's a little bit with the times. So let's have a look on correctness. So in this section, we state our correctness and security theorems. We consider clients and the server A execute the doubly homomorphic secure aggregation with inputs masked and clients. Okay. The correctness here we provide a precedent statement of correctness prior to the security analysis. So the correctness theorem: if participants and end client follow the homomorphic model aggregation protocol, given that the masked seed K0 returned by the masked seed aggregation protocol, client can obtain MU with negligible noise. Okay. Proof: because the selected pseudo-random generated is almost seed homomorphic, we have for the homomorphic model aggregation protocol. So this is the noise here is insignificant relative to the domain of aggregated quantized model update, which is and can be demonstrated to have a negligible impact on the quality of the trained model experimentally, we conclude that the model aggregation can be computed correctly based on the given K0. So this is for the correctness. Then for the security, then we show that the doubly homomorphic secure aggregation achieves the two aspects of security goals set for the cross-silo federated learning as described in section 2.4. Okay, we prove our schema is secure against the server clothing with up to numbers to clients in the honest but security setting. Those clients are the server learn nothing more than their own inputs. Okay, and the sum of the input masking seed and masks of the other clients. Note that for the ideal aggregation schema, if the server corrupts a set of clients, the partial aggregation result of the remaining clients will be disclosed as well. The information obtained by the clothing participant is our schema is the same as the ideal case. Meanwhile, the security guarantee is established on the setting without a TTP, where intermediate model data is visible to the necessary parties involved. We consider the execution of doubly homomorphic secure aggregation with privacy threshold and underlying cryptographic primitive are instantiated with security parameters. In such a secure aggregation execution, the view of a client view consists of its internal state, including its model update, masking seed, the masking seed, individual key pure for multi-K BFV, okay, the aggregated model update and all messages this party received from other parties, including common public key, ciphertext CT and CTR. The view of the server A consists of the received information, including the individual public key, the ciphertext, the partial re-encryption share, and the masked model updates. The message sent by this party will not be part of the view because they can be returned using the other element of its view. Given any subset be a random variable representing the combined view of all parties in V in the execution of the doubly homomorphic secure aggregation, where the randomness is over the internal randomness of all parties and the randomness in the setup phase. We show that for any such set V of honest but curious clients of size up to n to the joint view of V can be simulated given the input of the client in V and the sum of the input masking seeds and the mask of the other clients. So this is the theorem of the security. Then this is the experimental setting. So the benchmarking models, we implement three representative machine learning application in federated learning and perform plain aggregation and doubly homomorphic secure aggregation for each one. Our first application is a CNN model consisting of two convolutional layers with a total of about 0.2 um, parameters trained over the fashionist dataset, and another application we train ResNets with parameters on the Safar 10 dataset, and the third application we use Shakespeare dataset to train a customized LSTM. Okay, parameters. The two applications are based on different type of machine learning model of various size and cover the learning tasks for image classification and text generation. The optimization approach for federated learning is the federated averaging algorithm. Okay, The optimization approach for federated learning is the federated averaging algorithm. For plain algorithm, the model updates are represented by real valued vector of um 32 bits and uploaded for aggregation without encryption. For the doubly homomorphic Skew aggregation before being encrypted, the bounded model weights are quantized into 16 bits unsigned integers. Homomorphic model aggregation protocol implementation. Okay, so this is the first part. In our implementation, we set the baseline setting of parameters of the set homomorphic pseudo-random generator used and the homomorphic model aggregation protocol as. So this is it. Those are table 1, comparison of privacy preserving approach federated learning system. So we have security and efficiency. Okay, we have the double mask, batch script, TP, and Poussin and ours. Okay, so this is just okay, so those are those are the inputs. Then the masked seed aggregation protocol implementation, we set the parameters of the multi-k BFV as n log 2 T, which is with set security. The masked can cover the computation domain of the masking seed agreement process. For the running time examination, we set the number of the masking seed pairs agreed during per execution of masking seed aggregation. Note that we can select larger to gain higher efficiency. All experiments are run in a Lenovo server with the configuration of the core is set NVIDIA GeForce. We implement the NGO, which built on top of Latigo, an open source library for Lattice. Okay. I will open those references to see if I have access to the code. Then here they discuss the efficiency of doubly homomorphic skew aggregation. We evaluate the efficiency from the aspect of communication and computation overhead and compare the result with two state-of-the-art method. State-of-the-art, okay, batch script and Poisson done. So okay, they compare this with those two ones. Crypt optimized the efficiency of homomorphic encryption-based Skew aggregation solution for cross-silo federated learning. Okay, optimize the efficiency of homomorphic encryption-based secure aggregation solution for the cross-silo federated learning. And the second one, utilize multi-K, which provide the same security guarantee with our method. We set the parameters of batch scripts the same as. So this is like the first technique. We set the parameters of the same as that in their paper and set the parameters of as. Okay, which ensure too much redundancy in computation and communication. Okay. Okay, all calculation below assume a single server and n clients where each client holds a model whose size is m. So let's discuss the computation, then communication, I think, efficiency. Okay, so we'll discuss the communication and, and the computation. Okay. So we first state the analysis of the asymptotic computation efficiency of each protocol and then conduct it with the running time of practical execution experimentally. We measure the running time of two protocols separately and the total running time of computation for one single epoch. We executed the tests 100 times and take the average. Okay, and homomorphic model aggregation protocol, the computation cost is mainly derived from computing secure homomorphic pseudo-random generator to generate masks for each entry in the model update vector. The computation costs for each client and the server are OM. We then test the running time for different model size. Since the selection of parameters influence the security, the number of clients the system can handle, and also the efficiency, we tested the running time under different setting of parameters of secure homomorphic pseudo-random generator. So we have the different setting of parameters, also the numbers of clients can influence the parameters influence the security. The selection of the parameters influence the security. So synthesis vectors are used for locally trained models whose elements are encoded to 16 bits unsigned integers, and the local training time and not including in the total running time the selected parameters setting and the corresponding running time of each client are shown in table 2. So this is it, running time of the homomorphic model aggregation protocol with different model size under different setting of secure homomorphic pseudo-random generator parameters. We have setting A, so this is parameters, this is the security, this is the maximum number of clients, running time for different model size. Okay, so that's when we increase u, okay, the security level will be enhanced. However, the computation overhead becomes larger. Where is it? In addition, larger P makes the system able to handle more clients while resulting in higher communication overhead, giving U either increasing P or decreasing Q will lower the security level. In this paper, we selected the most moderate set of parameters to conduct the following efficiency evaluation. We set the parameters to ensure sufficient security guarantee and avoid overflowing when the number of clients is below the threshold. Okay. And the masked seed aggregation protocol, we use multi-k BFV is utilized to encrypt masked seed where the length of each one is U. This is the length of each one, and the computation cost of each client is composed of 4 components. Okay, the computation costs 4 components. Generating encryption keys. Okay, this is the first one. The second one is encrypting the message, computing the partial re-encryption share, and decryption. For the server, the computation cost can be broken down into evaluating the ciphertext, addition operation in our protocol, and merging the partial re-encryption shares. The running time of masked seed aggregation protocol for each phase is evaluated, and the results of each step are listed in table 3. Running time of masked seed aggregation protocol. So we have the key generation for the client, encryption and aggregation, public key switch, final decryption. We have 4 stages. Okay, So note that the computation overhead of clients here does not depend on the amount of the model parameters and the number of clients. Due to the small data size needed to be exchanged, the overhead is relatively small. What's more, the masked seed aggregation protocol runs once per T epoch during the overall training process, whose average overhead is negligible. It reduces the number of communication rounds and can make full use of BFV backend technologies improve efficiency to evaluate the total computation overhead resulting from doubly homomorphic secure aggregation. So to the total computation, we compare the running time of computation for an integral iteration with plain federated average and the batch scripts and Posen in the plain federated average, the learning process without secure aggregation client trained the model for T local epoch before the plain model updates are aggregated by the server party. The running time here includes the time of both local training and aggregation, so it's less. For other Skew aggregation methods, an integral iteration includes T local epoch of training, encryption of the model update, aggregation of ciphertext, and decryption of the results. The total running time is evaluated with set n 10 applied to layer, okay, as shown in figure 5. Figure 5, figure 5. Okay, where is it? Figure 5. Okay, so listen, you are here. So our DHSA reduced the computation overhead significantly. Okay. The extra running time over the original federated average owning them is significant compared with the batch scripts, right up to 25 speed up for the aggregation. Okay, that's good. Specifically, when the size of the machine learning model increases, the computation overhead of DHSA increases more gently. DHSA gains a greater speedup over the baseline when the model size gets larger. Okay. Then we have the communication overhead. The communication traffic mainly comes from the homomorphic model aggregation protocol where the masked model of size M are uploaded. The communication cost is OM for each client and OMN for the server, equal to the plain learning of federated learning. Okay, for the MSA protocol, the inputs are the masked seed whose length is parameterized, resulting in a constant communication overhead depending on the selected parameters of the masked seed aggregation. So based on based on parameters n and q, we select for NKBSV, the public key and ciphertext size is about 2n log. The overhead includes 3 rounds of communication. The common public key is agreed in the first round, where each client uploads the individual public key. Okay.